Okay, dah start. Okay, Bismillahirrahmanirrahim. Assalamualaikum and good evening to our beloved lecturer, Sir Muhammad Al-Fatihi. So today, me and my team would like to present our project presentation. The title of our project is Renewable Assist Oil Production, the Optimization of Organic Rankin Cycle. So before we move further, let me introduce our group member first. First we have Mr. Khairul Iman, then Mr. Awang Amran bin Awang Herman, Muhammad Nafal bin Sharizam, Arif Ashraf bin Azman, and me, Megat Firdaus. So without overdue delay, I would like to invite Mr. Awang Amran to present the first slide.
Alright. Okay. To understand our project, we first need to look at the current state of the industry. So petroleum extraction is incredibly energy intensive. As oil fields mature, the natural pressure drops and we have to rely on artificial lift systems like a huge pumps to bring the oil to the surface. These pumps consume a massive amount of electricity, which is usually generated on site by burning diesel or natural gases. However, there is a hidden energy sources right in the pipe. In the high pressure, high temperature HPHT reservoirs, the crude oil mixture reached the surface at a temperature exceeding 150 degrees Celsius. This brings us to the core conflict of our study. Currently, this high temperature is treated as a liability and not an asset. For the safety and the flow assurance, we cannot transport the oil at 150 degrees Celsius. We require to cool it down below 60 degrees Celsius before it enters the pipeline. So what is the current industry practice? We use the air coolers and the cooling towers to reject this heat directly into the atmosphere. And this significantly creates three thermodynamic irony, which is the waste, the cost, and environment. So we are dumping a high-grade thermal energy into the air and causing massive exergy loss. And we are burning fossil fuels to power our pumps, and this increase our carbon footprint. So our project asks a simple questions. Why we dump this heat when we can use it to generate the electricity we need? So to answer these questions, we establish four specific objectives of this project. First is simulations. We aim to model an organic Rankine cycle systems using MATLAB integrated with CoolTrop libraries. This allows us to accurately calculate the thermodynamics properties of the fluid. Second is optimizations. We conducted a parametric study to find the sweet spot. We analyzed how changing the evaporator pressure affects the overall thermal efficiency of the systems. Third is the critical evaluations. We compare the past with the future. We evaluate the legacy working fluids R11s against a modern sustainable alternative R245FA. Crucially, we wanted to quantify the benefits of adding the recuperator to the cycle to see if it improves the efficiency. And finally, the sustainability. Our goal is to propose a solution that isn't just efficient but compliant. We ensure our designs aligns with the safety standards like API 617 and the global environmental goals like the Montreal Protocol. So for the next slide, I would like to invite our next presenter, Muhammad Nafal.
Thank you, Awang, for inviting me to the presentation. Now I'm going to talk and explain in detail about the system that we use for our project. Actually, there are two types of system that we want to design, but we only use one. For the first one is ORC system, and the second one is SRC system. So what is ORC? ORC stands for Organic Rankine Cycle, and SRC stands for Steam Rankine Cycle. So instead of SRC, why do we use ORC? So for steam Rankine cycle, it requires more massive heat. Since our heat source is only 160 Celsius, we use organic fluid like refrigerant because they boil at much lower temperature than water. So for the efficiency for for ORC system, the efficiency is high because this fluid has a higher molecular weight, which allows the turbine to extract more work even at this lower temperature. Next. Next, going on to the fourth stage of process. As shown in the slide, we have 4 stages, which the first one is pumping, second one heating, third one expansion, and the last one is cooling. So what happened in the first stage? So the liquid is pressurized. It requires small amount of work input to set the liquid into high pressure evaporation. Moving on to the heating stage, the high pressure liquid absorbs the heat from the crude oil and transform the liquid into vapor, but with high pressure and high temperature. Moving on to the expansion, at the third stage, we call it as the power stroke. The vapor expands rapidly, spinning the turbine to generate electricity. We assume for the isentropic efficiency in about 92%. The last one, the cooling stage, the vapor is cooled back down into a liquid by an ambient air in about 25 Celsius, completing all the loop for the 4-stage process. Next. Moving on to the simulation and tools. For this project, we use MATLAB as our engine, and we use database of CoolProp. So instead of using ideal gas law, which is often inaccurate for organic fruit, we have integrated the CoolProp library. So as you guys can see in the coding, we have the first state, which is superheated or saturated vapor. The second state for turbine outlet, which is isentropic expansion. And the last one, we calculate the efficiency. So for this database, we use Helmholtz energy equation, which allow us to track the fluid property, enthalpy and entropy, with high accuracy near the critical point where the fluid behave unpredictably. So when we ran the interactive loop, it showed that the pressure range is about 20 to 40 bar, which is optimum pressure for the system, where the power output is maximized without damaging the equipment. That's all from me. Now I'm going to invite our next presenter to continue the slide.
Okay, thank you, Manafal, for the explanation. So now I will moving on to the simulation result for our project. So for this project, we have decided to use two type of working fluid, which is the R11 and the R245FA. So for the first working fluid, which is the R11, so the graph that you can see here is the graph that we have been able to achieve from the standard cycle and the recuperated and with the cycle that we incorporate the improvement, which is the recuperator, which I will explain in the further slides. So as you can see from the graph on the left, as you can see the dash line, the red dash line represent the standard cycle, which doesn't incorporate the recuperator, and the blue line is the cycle in which we incorporate the improvement, which is the recuperator. So as you can see from the graph, you can see that from the pressure of 20 bar to 40 bar, you can see that the thermal efficiency is decreasing. So this happens because for R11, 44 bar is the critical pressure for this type of working fluid. So as the working fluid get closer to that critical point, the latent heat or the heat, the energy that required to boil the fluid shrinks rapidly. So this hurt the cycle ability to absorb heat efficiently. So as you can see from the table on the right, you can see that for the standard efficiency, for the standard cycle,
and at the bar pressure of 20, the thermal efficiency is 22%. And when we incorporated the recuperator, which is the improvement, the efficiency increased by a margin of 0.1%, which is at 22.1% at 20 bar. So moving next to the next slide. So this is the TS diagram for the working fluid of R11 before we incorporate the recuperator. So as you can see, starting from the left, you can see at point 3 and point 4. So this vertical line, there is a vertical line here, but the increased temperature is so small, so the vertical line is almost impossible to see, but there is a vertical line here. So the vertical line represent the process of the pump, which is the cycle in the process which we will pump the organic fluid into the cycle. So this is the pump phase. So next we can see that from 4 to 1, this is the process of the boiler of the evaporator. So this is where the organic fluid is given the heat energy, or it is boiled until it reaches the saturation temperature, liquid temperature. So, and then it will turn into a mixture until it turns into the saturated vapor. So the liquid will we will heat the organic fluid until it reaches a saturated vapor phase, and then we will it will move into the turbine. So you can see it will enter the turbine as a saturated vapor and exit the turbine still as a saturated vapor. It might not be 100% saturated vapor because it is under the dome. It might be exist as a mixture, but mostly it is exists as a saturated vapor state. So, and then from 2 to 3, it will move into the condenser, which the excess heat, the waste heat will be removed. So the next slide. So this is the TS diagram of the working fluid R11 after we incorporate the recuperator. So as you can see, that the diagram doesn't change as much from before the improvement. So this is because that if you remember that after the working fluid, after it passes the boiler and into the turbine, the inlet of the turbine, it enters as a saturated vapor. So and then it exits also as a saturated vapor. So there is not a high amount of waste heat that the recuperator can use to preheat the organic fluid before it enters the boiler. So that is the reason why when we incorporate the recuperator, the efficiency only increase about 0.1%, because that is not enough waste heat that the recuperator can catch from the exit of the turbine. So next. So this is another type of working fluid. So this fluid, the name of the fluid is pentafluoropropane, or commonly known as R245FA. So as you can see from the graph, so this graph represents the thermal efficiency versus the evaporator pressure for before the improvement and after the improvement, which is before we incorporate the recuperator and after we incorporate the recuperator. So as you can see from the graph, you can see that the red dashed line, the standard cycle, the efficiency peak about at 90%, and when we incorporate the recuperator, the efficiency increase about 22 plus percent. So this is you can see that the difference between the dashed line and the blue line, so this represent the excess or the waste heat that exit the boiler. So why does the R245A FA have so much waste heat? Because it is a dry fluid, meaning that when it exit the turbine, it will exit as a superheated vapor. The state of the ergonomic fluid that exit the turbine will be in a state of superheated vapor. So there is a higher amount of waste heat that the recuperator can absorb from the turbine exit. So the next slide. So here is the recuperator itself. So this is the image of the recuperator. So as you can see, the recuperator is a device that we can incorporate in an organic Rankine cycle to capture superheated vapor which exit from the turbine the turbine outlet. So we will use the waste heat from the turbine outlet to preheat the liquid of the organic fluid before it enters the boiler. So the advantages of this that the advantages of this is that we can reduce the fuel consumption of the boilers. Hence, we can increase the efficiency of the whole organic Rankine cycle. So as you can move on to the next slide. So as you can see, this is the TS diagram for the working fluid of R245FA. So as you can see, when it enters the turbine inlet, it enters as a superheated vapor. So, and then when it exits the turbine at point number 2, you can see that it exits as a superheated vapor because it is on the the far right side of the saturation dome. So you can see the blue line here from the 2 and the saturation dome. So this represents the excess or the waste heat that exit the turbine outlet. So the recuperator can absorb this waste heat and use it to preheat the organic fluid that comes out from the pump before it enters the boiler. So it will we can reduce the amount of energy for the boiler to heat the organic fluid because it is already preheat after it exit the turbine outlet. So we can move to the next slide. So as you can see here, when it exit the turbine outlet at point number 2, you can see there is a dotted dash line, pink dotted dash line here. So this represent the cooling of the organic fluid that that flow out from the turbine outlet. So this dash pink line is represent as the cooling because the heat from the organic fluid is being absorbed by the recuperator to preheat the organic fluid that is flow from the pump. So that is why we can see that the line here will be is a dash line. So that means that after 2, the liquid will be cooled because the heat from the turbine outlet will be absorbed by the recuperator, and then it will straight go to the point number 4 dash. So as you can see that when it enters the boiler, it already have already hot. It's already increased in energy because it already absorbed from the turbine outlet energy, that is the waste heat. So and we have simulated that for when we incorporate the recuperator, the optimal operating point, which is the optimal pressure for this cycle, is at 26.6 bar. So by using this pressure and by incorporating the recuperator, we can achieve an efficiency of 22.2%, 22.1%. So it exceeds a higher, the margin of efficiency is higher when we use a different working fluid and when we also incorporated the incorporator. So from 19% efficiency, we can increase to 22.1 efficiency. So that is all from me.
Stop, Matt. Thank you, Ashraf, for very detailed explanation. Next, moving on to our critical evaluation. We perform a direct comparison between the legacy fluid, which is R11, and our modern choice, which is R245FA. So first, looking at the sustainability terms, R11 is a chlorofluorocarbon with a high ozone depleting potential, or ODP, of 1.0, which is why it is banned. So in contrast, the R245FA is a chlorofluorolefin or penta pentafluor pentafluoropropane with a zero ODP, making it fully compliant with the current environmental standard. So if we can see for the thermodynamics perspective, we found a distinct difference at the turbine exit, which is the R11 exit, the turbine only slightly superheated, meaning there is not much waste heated left to turbine to capture. However, the R245FA is a dry fluid that is it as a highly superheated vapor. Then this brings us to the recuperator. For R11, adding a recuperator offer only a marginal gain. But for R245FA, the recuperator is essential because it captures that high exhaust heat and recycle it. So by using the R245FA with the recuperator, we achieve a higher maximum efficiency of 22.5%, surpassing the 22.1% of the legacy fleet, which is the R11, while remaining the environmental safe. Next, I will invite for the next presenter.
Okay, thank you, Megat. So now we move to our proposed improvement. The primary technical enhancement we are recommending is the integration of a recuperator into the organic Rankine cycle. Through our MATLAB simulations, we found that for the modern fluid R245FA, adding a recuperator is a game changer. It increases the overall thermal efficiency from a baseline of 18% to 22.5%. To put this into perspective, in a 1 megawatt power plant, this 4.5% efficiency jumped to an additional 45 kilowatts of power output using the exact same amount of heat input. From a business standpoint, this makes perfect sense. At standard industrial electricity rates of 10 cents per kilowatt hour, this system saves over $39,000 per year. This level of savings allows the operator to pay off the heat exchanger hardware very quickly, making it a highly cost-effective upgrade. So next slide. Next slide. Okay. Beyond the technical efficiency, our project is deeply aligned with UN Sustainable Development Goal 13 for climate action. First, let's look at the environmental impact. By validating and choosing R245FA, we ensure the system has zero ozone depleting potential, which is a significant upgrade over legacy fluids like R11. More importantly, this system acts as a massive carbon offset by replacing traditional diesel generators with this waste heat recovery system. A 1 megawatt plant can prevent approximately 2,365 tons of CO2 emissions every single year. Safety is also a top priority. Our design adheres to API 617 standards for turbine reliability and ASME B31.3 for process piping to ensure the system can safely handle the optimized pressure of 26.6 bar. while R245FA is non-flammable. It is heavier than air. Therefore, our safety proposal includes the installation of oxygen depletion sensors to protect personnel from any potential asphyxiation risk in low-lying areas. So now I will invite Megat to conclude our project.
Okay, thank you, Naiman. So to conclude our project, we have determined that the system is feasible, and recovering waste heat from crude oil at 160 degree is a viable method for generating on-site power. And we have identified the R245FA is an optimal working fluid. It is a superior choice, delivering 22.5% thermal efficiency and ensuring full environmental compliance. Also, our simulation also define the optimized parameter for this efficiency. The system should operate at a pressure of 26.6 bar. We must not exceed this to avoid the operating too close to the fluid critical point. And additionally, the recuperator is identified as a critical component to successfully recover energy from the superheated exhaust. And then ultimately, this project successfully convert a waste stream into a value stream. It reduce operational costs, which is OPEX, and directly support the industry transition toward net zero operation. I think that's all from us. Thank you.